Good morning. Thank you, Monica. So I'm going to start with a weather report at UC Berkeley right now. The temperature is 16 degrees Celsius with a 21% precipitation chance, 64 degrees of humidity, and light winds at 29 miles per hour. So wind advisories on the Bay Bridge, very important for traffic. So I'm going to talk. So first, thank you, Monica. Thank you to the IPAM organizers and Christian. And it's nice to see. It's kind of strange to see familiar faces through Zoom, assuming I actually was going to go to UCLA. But thank you for being able to translate this program digitally. So today I'm going to talk about Lagrangian control, and like we heard in Maria-Laura's talk and previous talks as well. And I'm going to try to almost show no equations in the entire talk. So that might be the last time I'm allowed in the IPAM building ever for the crime of not showing too much math. The high-level motivation of this is mixed autonomy. There's various forms of future transportation that make the news all the time, things like car tube, Hyperloop, and whatnot. The truth is, in the field of automation, some of the most conservative forecasts predict that there will not be full autonomy level 5 until 2075. And people giving these kinds of forecasts, like Steve Schladover, have over 30 years experience in the field. So I think that means that we are probably in for multiple decades of mixed autonomy, where manned vehicles interact with, or people-driven vehicle interact with self-driving vehicles or vehicles with some certain level of automation. And part of the questions that arise in mixed autonomy or full autonomy is whether that impacts the energy footprint of congestion in a positive or negative manner. And this graph, which was produced by Don McKinsey, really on the basis of very rough first order estimates, show that some aspects of autonomy or mixed autonomy can be positive, like platooning, but combined with others, such as higher speeds, for example, could potentially steer the system to a more efficient system or less efficient system. And that's kind of the motivation of the work that we're doing here, and I'm going to present today. Now, as you've heard through the program and through Maria-Laura's talk and the previous talks, there's a variety of models that are used in the field of transportation. For example, the work of Carlos, of Monica, uses microscopic models. Obviously, in the practitioners' world, microscopic models have been around for over 20 years. And while their accurate use might have appeared like science fiction 25 years ago or 20 years ago, when there was very little data or even compute power to calibrate them, I think with the increase in computing and data, I think these models are going through a rebirth. And there's even further models like agent-based simulations that now, with even finer granularity of the data, such as individualized activity data, have pushed that paradigm even further. And so this talk really operates at the level of microsimulation because of our firm belief that in this decade, we will see enough rise in computational power, data, and machine learning to not only calibrate them, but use them efficiently. All of you are familiar with microscopic models, but just for people to be on the same page, when we use microscopic models, we mean realistic enough simulation environment, so whether it's Sumo or MSUN in our case, realistic map, so something that is actually built from OSM or Navtec or TeleAtlas or something real, and which has enough attributes to influence the dynamics of the models. So for example, the lane width, the curvature, which come with specific dynamics models, and of course, vehicle classes, like you can see here, trucks versus other types of vehicles. And the battlefield, as we see it in this domain, in the domain of machine learning and application of machine learning to mixed autonomy or full autonomy, has various frontiers that are of interest. We're not right now interested in data, though, for example, the test bed that Dan Work is building in Tennessee will definitely push the frontier of data much further. by adding very high resolution video. So in a sense, bringing an NGSIM second generation to the community. But this is not work we do here, even though we will hopefully very strongly rely on that work. On the other hand, calibration is something that we will be working on based on that data. And there is clearly an issue about model computation, because one of the issues of machine learning algorithms is that there is often, depending on the approach you use, the need for hundreds of thousands of runs so the algorithm can learn. And that is not trivial with microsim, which is why I think macroscopic models still have a bright future, and including in machine learning, like, for example, the models that Maria Laura or Paola, Benedetto Piccoli, and Carlos, and many other have used, can also be used very efficiently for training. So it's not that one comes at the expense of the other, but it's that in some circumstances, it's still going to be, for the decade to come, way too expensive to run microscopic models in training, and therefore there is a need for potential hybrid approaches. Of course, in the control side, what I'm circling here with my mouse, assuming you see my mouse moving on the screen, is there's an endless list of approaches in machine learning, many of which are experimental, that are of great interest in terms of the things that could be done to improve traffic. So the political program, if you will, of this work is really being able to continue establishing a framework that we've now started several years ago with the work of a PhD student who is now a faculty at MIT, Kathy Wu. We called it Flow when we launched it, so that it's an integration of machine learning and in particular deep RL with microsim on AWS EC2. In the specific context of mixed autonomy traffic, so again, this notion of interaction of manned or people-driven vehicle with autonomous vehicle, and the notion that we would like to demonstrate actual migration, so some form of transfer learning on some hardware within the next years to come, not the decade to come, but really years to come. And that's something we do very closely with John Sprinkle in Arizona and Dan Work at Vanderbilt. So I think we always have to worship our past, and our past started in 1935 with this picture that I'm sure you've already seen hundreds of times by now. So no need to introduce Bruce Greenshield and the famous traffic jam that led to the fundamental diagram. This movie you probably have seen dozens of times, so probably doesn't need an introduction. Also, this is the Sugiyama ring experiment. One thing which is interesting to point is that obviously it took several decades between the 35 first measurement of traffic jams and the kind of a first experimental record, if you will, of stop and go waves. And of course, my rock stars, Benny Siebold, John Sprinkle, Benedetto Piccoli, and Dan Work, and Maria Laura, I should add a picture here, because I think that was her controller that was running in that particular movie. But this experiment was also seminal in that it still took 10 years from 2008 to 2017, but this is the first, to my knowledge, record of mixed autonomy control. And of course, the fantastic numbers that Maria Laura showed in the previous talk are very inspirational to the whole community, that this type of work could be done at very large scale. Of course, at the time these results were becoming known to the public, one of our students, Kathy Wu, so MIT prof now, was trying to replicate these in simulation. In Sumo, which, as we know, and Benny Siebold is actually quite helpful in that respect, it's quite difficult to recreate waves in simulation, because the instabilities and the theory that we saw in the previous talks are not necessarily captured by simple models that run in this software like Sumo. But the interesting part that came out of Kathy's work was that she was able to reproduce the waves, so which is just I guess a technical calibration issue, but then at some point managed to replicate the controller that we just saw in the experimental movie, the 2017, I believe, Arizona test, and stabilize the flow. But there's a major difference in these two approaches, is that the 2017 experiment, to my knowledge, relies on follower-stopper approaches and model-based approaches, so either explicit or at least mathematical, which require, in a sense, having a model of the vehicles. The 2018 work she did is model-free. That's model-free deep RL, which essentially only uses simulation without any knowledge whatsoever of the vehicle's dynamic to achieve the same type of smoothing. And that result was actually fairly disturbing to us, not only because it did reproduce in simulation. Obviously, this is not an experimental test, so nothing in complexity compared to the Arizona thing, which was really a fantastic breakthrough in the history of the field. But what it was, the reason why it was disruptive to us is because suddenly it became clear that you could do the same as what the entire mathematical community had done without any model. And that is disruptive and that is disturbing. I mean, if you think about the production of articles in the field from the inception of the field in 1935 to the first experiment, I mean, we did a rough count and saw over 10,000 articles. And even then, the analysis of the waves, the analysis of the instabilities, I mean, depending on how broad you look, you can see this is, again, about 1,000 articles. And then in one article, Kathy was able to reproduce the same result, zero proof, zero guarantees, and even I could say very little understanding of why this is working, but the same efficiency. And that was the pivotal point for us in our work, because we were looking around at what people were doing in robotics. You might have seen the fantastic movies of the folding towel robots of Peter Abil, and many other things happening in the field of robotics and experimental robotics. And then it became clear to us that custom designing reward functions and using state-of-the-art reinforcement learning algorithms could be very promising for the field. And that was, for us, a very interesting thing we wanted to pursue. And so we launched the program called Flow, which is this interface of deep reinforcement learning, microsimulation on the cloud. And so I'm going to show a few of the early achievements of this before I go to what we're doing now. But just for the sake of the presentation, every time you see a red vehicle, you can assume this is going to be a self-driving vehicle, so some level of automation. When there's no lane changes, it's mostly longitudinal, and in some cases, it will also have lateral. When you see a blue vehicle, that's a vehicle that the red vehicle can sense. So if I'm a red vehicle, I can sense. So in that case here, you could sense in front of you and behind you. So assuming, you know, Tesla has 6 cameras, so assuming you can use both sets of cameras to sense the people in front and behind you. And then the white vehicles are vehicles that are following typical human behavior. So take your favorite car following model, IDM, Bondo, whatever you want. But the point is that the red cannot see them, the blue cannot see them. Obviously, they can sense this indirectly because information propagates through traffic, but they live their life, you just see their effect. So the mixed autonomy framework we're using essentially amounts to understanding what type of algorithms should the red cars be running when they're only sensing the blue cars, and in some cases, communicate between them or not. So the red vehicle could communicate with another red vehicle if you need a form of centralization of the optimization and control, or not if you have a completely decentralized scheme and multi-agent scheme. So we don't have any prerequisite assumptions there. It really depends on the cases. And so typically what Kathy did later in her work was try to experiment what would happen if you tried this on different settings. So for example, this setting you see here is a double ring where the car is clearly behaving like a total jerk, preventing people behind it to cross it. And thereby, by an interesting combination of longitudinal speed control and lateral lane switching, is able to stabilize a double ring. And the interesting part is that, you know, there's a lot of work in the early 2000s, Jorge Laval and many others in lane switching. And lane switching is difficult because it's a discrete variable. And so you have to take into account the combinatorial explosion of the lane switching. So it's very hard to do. But what's interesting here with the reinforcement learning is that it does learn how to do it. Of course, it's not very realistic that it would happen, but it figures out the way to use the lane switching without suffering from that combinatorial explosion that you typically see. And you could argue, well, okay, so on the other hand, this is something that is simple that you could have anticipated. You learned that in police academy. Okay, and it is actually true. And so the takeaway message here is that in some ways, the ML algorithm has reproduced what the human learned to do with different paradigms. And so that opens this notion of emergent behaviors, if you will, which is a common concept in many subfields of robotics, where algorithms, machine learning algorithms, somehow are able to learn what humans learned since they were born, and then potentially surpass them, which is the big motivation for this work. So obviously, surpass them, something like this is aspirational. That's obviously not real. But if you try the same approaches on things which are slightly more complex, like this 8-figure, if you just have the typical car following models, what will happen is the cars will stop at the intersection, let each other pass, which is probably the worst way to maximize, well, essentially they're going to way to minimize throughput through the intersection while maintaining safety. And the interesting part is that if you train the same algorithm I showed before on this scenario, then what the ML algorithm does is it actually figures out the proper speed at which it should drive so that the IDMs or car following models or whatever you run on the non-automated vehicles automatically space themselves at the right distance to maximize the length of the snake so you don't have to stop. And that's interesting because the algorithm does not know the models of the blue cars. So in other words, I'm going to just replay the movie. The interesting thing here is that you could ask this as a homework or exam problem, like compute the proper spacing for this, and then from that deduce the speed, and therefore figure out at which speed you should drive to achieve that effect. But the interesting part is that the ML algorithm learned that without having any notion of the models of the IDMs. All it did is figure out that if it achieved that speed, it would produce the maximum throughput. Also, full disclosure, all the cars are blue. So for this to work, you need to see every other car in the queue. So, okay, there's no free lunch. To our knowledge, we've not managed to make this work if you don't observe what people are doing behind you. So, it doesn't work all the time. But again, in 10 years from now or 15 years from now, when most cars are connected, that won't be an issue anymore because hopefully that data becomes available. So essentially, this is a case where the emergent behavior started from a trajectory diagram like you see here, where cars wait for each other at the intersection, to rediscovering a form of platooning in this 8-figure. So it's another interesting emergent behavior. Another case here is if you try to maximize the throughput at an intersection. And so here, if you don't do anything, every car is just unobserved. What you have is essentially a situation where people let each other pass. And that's, again, the most inefficient way of achieving throughput in the merge here. If I launch the exact same algorithm now with some proportion of automated vehicle that can sense blue vehicles, then it's much better. You can just look at the throughput, but I have really no idea what it's doing. And that's interesting because that's a case where I cannot even post facto rationalize what happened. So the blue car the red car can sense all the blue cars, which have been somewhat randomly selected. It doesn't know anything about the white cars, other than if it's run into it, it's not going to crash. And essentially, it's able to maximize throughput that I can see, or at least improve throughput. But I have no idea why it's doing it, and what it chose, and when did it decide to stop the platoon, to continue the platoon, and so on and so forth. So this is an interesting example of a great improvement in energy efficiency. I would say at the cost of explainability. There's this subfield of machine learning, which is called explainable AI, where people try to understand what's happening in the reinforcement learning, and that's a case where so far we've not found a good explanation. So then there's a lot of other things you can do with this. For example, transfer learning is the process of learning in one setting and deploying it in a different setting. Obviously, that's a big challenge because part of the shortcomings of machine learning is that sometimes it's really not clear how an algorithm will perform in a situation it has not seen before. So we tried that as well because as we learned from Maria Laura's presentation and also from Benny's work and Benedetto's work and many people's work, the dynamics that we observe in the ring has features that translate to a single lane road. And so what we try to do is see if we could train agents in the ring and deploy them in a merge, a situation that the algorithm has not seen before. So we did it, the algorithm converged. Again, no guarantee, no proof, no nothing. I mean, today is a no equation day, so just fun. So the example we were looking at here is this merge where once in a while you dump a car in the merge. So obviously it creates these back propagating shock waves that most of you are familiar with. And you can see that wave, I don't know how fast and the movie is playing on your screen, but you should see these cars accumulating in the back of the merge here. All of you know this, it's hyperbolic. In essence, if you perturb this, the characteristic will move backwards if the density is high enough. And you can see this back wave that now it's propagating backwards. It's about 2/3 of the way, and soon it's going to reach the other end of the screen. So if you apply the same algorithm here, but training it on the ring, deploying it on the road, so you can see that progressively as you follow the red vehicles as they come, they start to slow down more and more. And this one, if you see it, it's now stopped. So I'm going to just pause here. This car has stopped. It's the car has transformed itself into a red light, essentially. It has learned to be a red light or a very, very slow moving variable speed limit in order to reconnect with the blue vehicle around the time it gets off the domain. And here's another one here. And so that's interesting because here's another one transforming itself into a red light. And so that's interesting because it has essentially learned something from the ring and successfully deployed it on the road. So if you look at the trajectory diagrams here, what you have is every time a vehicle enters here, you have to add a trajectory. So there's a new mini trajectory that starts at post mile 600. And if you do nothing, then you have the typical shock waves that, or any good model should produce, whether it's a microscopic model and it's essentially a form of string instability, or if it's a hyperbolic PDE model, then it will be a shock wave. And so the point is that the interesting feature is that this car actually learned and therefore preventively slowed down so that by the time it crosses the entry point, it reconnects with a stream of vehicles. No, there's no magic here. In order to do that, it has to know the position of the corresponding preceding blue car, because otherwise it wouldn't know how to do it. So there's still that need. But what's amazing is that it essentially deployed a feature it learned in a different context to that new context. And it's also very promising here. So the students who did this, Eugene Vinitsky and Abu Dikraidier, were pretty excited because their work was initially picked up by Science. And they showed at the time, and now we're talking about 2 years ago, that this was extremely promising. And with 10% of AV, essentially for that setting, they could smooth traffic. Now, this is still not a real road. This is not even a micro simulation of a real road. So just, I kind of dance and celebrate the results. At the same time, acknowledge that at this point, it's just an enhanced simulation. But this was very promising. And that was the beginning of a project that we're now leading with Benny Siebold and John Sprinkle, Dan Work, and Benedetto Piccoli. It's a Circles project where we're going to try to do this in the real world to smooth traffic with real cars at scale. And for me, this result here was very inspirational because that was one of the motivation to start Circles. Obviously, the goal and the aspiration is to be able to operate on things like this. And it's so I'm sure you've seen these movies, so they're quite famous in the community. But the idea is that if you're able to smooth phantom jams, that's going to be already a very big achievement in the field of traffic flow management. And so that was the beginning of our new, or not so new now, it's been a year now, our project Circle. And the idea is to take these results and the other results that the other PIs have produced using PDs, using ODs. I mean, there's really want to be a completely algorithm and approach agnostic. But the idea being to show that we can demonstrate that in the real world. And so there comes again the notion that if we're going to do this, we should be able to demonstrate these results now in a real microsimulation model. And by that, I mean some model where the map is somewhat realistic and differentiating between all the classes of vehicles and dynamics and reaction to the topography that I mentioned earlier. And so when we started Circles, we were fortunate enough to inherit the I210 model, which had been built by the Connected Corridors team here in the backyard of UCLA. That was our starting point. And obviously now with the big projects that Dan Work is leading in Tennessee, we'll probably migrate these results to I-24. But nevertheless, the I-210 work was really good for us to get started on this. And so to give you a sense of what this is looking now is if you follow the same color scheme, essentially what the team is doing is producing these shock waves, which we routinely observe on 210, and trying to see how the algorithms we've proposed can adapt to that. Benny and Dan are part of what we call the WAVES team, which produces these simulations and on which the rest of the team experiments with algorithms of all kinds and nature, and in our case for Berkeley, the reinforcement learning algorithms. And so typically what you're looking at here is trying to, so if you do it lane by lane, ignore the zero for now, trying to reproduce the things that I showed in simulation here. And you can see that if I just flip back a few slides to these beautiful results, or even these idealized results, obviously already, even in the digital world, reality is much harsher, and it's actually not that easy. But we've been very happy to see a lot of progress already that makes us believe that the same will be possible to do in real life. And so right now, what a lot of the people in the team are doing is trying to experiment with these models and see how these waves can be smoothed. In fact, today at the end of the talk, I will try to show some results on the dashboard where we benchmark algorithms against each other. So this is kind of, in a sense, what a smoothed fundamental diagram, or sorry, a time-space diagram would look like after you've smoothed the waves. And of course, it's not all beautiful, all green, because life is obviously very messy. And an interesting thing, as I was mentioning earlier in experimental robotics, is that a lot of that work is experimental in nature. So unlike algorithms and the beautiful theory that can prove performance up to a certain point or robustness or stability, we can't do anything about this at all. And in fact, if you try to minimize the energy consumed by the system, algorithms, you can trust them, they'll do something really stupid. They'll just stop all the vehicles. So that's the best you can do, right? If you stop all the vehicles, then you don't spend energy, and that's fantastic. So a lot of that work is experimental in nature, in that, in fact, energy might not be at first glance the proper metric to use if you want to optimize energy. Maybe what you might want to do is to try to minimize some form of infinity norm of acceleration over a certain period of time for all vehicles, with a hard constraint on the VMT. And so this is where, in a sense, the trial and error comes. And a lot of our work consists exactly in that. It's like saying, well, maybe if you are going to minimize energy, you still to have another penalty term, so cars keep swimming. And that's why, I mean, on one hand, we're all very excited about the amazing things that reinforcement learning and machine learning can do for us. On the other hand, if you're not careful, they produce things which are strange but explainable, like, okay, just stop all the vehicles and you'll do better. In other settings, we're also using different types of problems. So this one was flow smoothing, and again, acknowledging Benny and John and Dan and Benedetto in the team. We're also working on other approaches where we are essentially trying to see if we can use Lagrangian control for bottleneck capacity improvement or throughput improvement. So top picture being like a typical double bottleneck going from 4 lanes to 1 lane, and the bottom one being the same, where now an algorithm selectively holds queues so that it never jams here. So that's another one which is interesting because there's all kinds of different architectures to support them. Would you sense all vehicles? Can you sense this chunk by chunk? Should you sense the density downstream, upstream? So there's lots of different information architectures that can be used to it. And in some cases, not all cases, you can see that the same algorithms in reinforcement learning essentially manage to do that. Obviously, the ultimate goal being to do it on the more realistic setting. So this is a microsim model of the actual Bay Bridge, the post-toll section with the metering light here. This is not done yet. I mean, we're still working on this, and it's actually way harder than we initially thought. So obviously, there's still a lot of work to be done. Now, part of what we want to do with circles also is transfer learning, where the transfer now reaches out to hardware. So we started working with Andreas Malikopoulos' team at University of Delaware, and it's working with Andreas and his team has been fantastic from the beginning because of the amazing platform they've built in Delaware. So what you see here is a comparison of the same algorithm on this roundabout, where the reinforcement learning vehicle are the blue vehicles and are essentially sequencing themselves, inserting in that roundabout. So I'm going to replay the movie from the beginning so you can see. Essentially, the control here is when do these guys enter the circle? So if you just do first come, first serve, which you will see on the left, then it will produce a certain sequencing. And if you don't do it that way, so you hold the vehicle selectively, then it will produce a different sequencing. And if you watch the military Hummer or whatever that vehicle is in the reinforcement learning scenario, you will see that it is the last vehicle to exit the circle, and it will exit long time, quote, before the last vehicle, which is here the Stanford purple car, oops, shouldn't have said that, exits a bit later here. And so that's another interesting achievement for us when we did that with Andreas's team. And again, working with Andreas was fantastic because they had already solved a lot of the architectural problems so that we could port our ORL algorithm. And the students who did this is Kathy Jiang and Eugene Vinitsky. Essentially, we managed to show that with the proper design of the reward function, we would be able to maximize the throughput, which was what we were trying to do here. And so this was our first baby steps in the hardware world, if you will. I mean, now with John's team in Arizona, John Sprinkle's team, we're able to access vehicles through the CAN bus. So putting this one step further, but this was also very promising for us moving network. So we've tried this on a different, this is Eugene, by the way, and this is Feng Yu, two of our students. So we've tried this on several platforms. These we call the babies. They're like $50 robots. And so what we're able to do is, again, these oscillations you've seen, smooth them. This was a demo we give in Washington. I'm going to just skip that. So maybe to kind of get this talk closer to a conclusion, I think the holy grail of this is, I mean, if I'm a fanatic fundamentalist person, I should try to get rid of models all at once so that I don't have to do modeling ever, but I can only rely on software that has good models built by experts. That's a fanatical view, obviously. I'll come back from the fanaticism in a minute. But the idea being that, in the reinforcement learning loop, if you have an action set that essentially produce some specific run of an environment, and if you can measure the reward, for example, minimization of total travel time or whatnot, then you can improve using your reinforcement learning loop. Now, in most of the cases, you also need access to the state space. So it's not just that the software would give you, okay, you did 33,000 hours vehicle on this set of the freeway. It also, usually, algorithms also need to ingest the trajectory of each of the vehicles to learn from them. And that's normal because, most of the algorithms, including some we have heard this morning, essentially look at the shock wave and try to remove the shock wave. But the interesting thing is that there is this field in machine learning called pixel learning, where you can actually learn from pictures. Or in a sense, you could view this as learning from rendering of traffic. So what if you decided to declare yourself blind to the state space? You don't want to access trajectory of vehicles, fuel consumption, position, speed, acceleration, forget all of it. Just access rendering of it, which you could argue the information is embedded in it. You could say that's really stupid. Why the hell would you do that? There's actually a lot of reasons why you would do that. First one being that the complexity of a picture does not depend on the number of vehicles in it. So in a sense, if I'm looking at a movie with 3 pictures or a movie with 200 cars, sorry, a movie with 2 cars, a movie with 200 cars, it's the same size of the image, regardless of compression issues. So the point is that the learning does not depend on the number of vehicles anymore. And the second reason why it might be interesting to do that is that deploying cameras everywhere is happening. So there is going to be cameras everywhere in the near future, especially on freeways. So the notion that you might learn from pictures without accessing the state space is actually strategically interesting. Because in a sense, I don't want to put the whole modeling community out of jobs because models are useless. But there is something to be said about if you could learn from pictures without building a physical model of a physical car, but a neural net model instead of the pictures, that might lead to an interesting generation of algorithms that rely on something different. And so we tried that. And so the notion is that essentially we figured out how to use specific rewards to do machine learning based on the rendering of the pictures. So we chose our 2 canonical examples, the ring and the 8 figures. But essentially what we did is the algorithms now, what they do is they ingest things like this. So you just don't feed them trajectories, you just feed them movies or rendering of what's happening. And so this can be done in a centralized manner, like on the left, or a decentralized manner, which of course is much harder. So if you try to ingest centralized information, essentially it's the same as you're flying a helicopter over the city or over whatever you're doing, and you're measuring everything which is happening, and you're using that to learn. And if you do it in a decentralized fashion, like on the left, then you assume that some vehicles can see around them. So once in a while, they'll see a vehicle, and they'll do something about it, and you learn from it. And of course, this is degraded information, so in general, it'll produce way worse results. But in a sense, if you could do this, then it's not a quantum leap to think that once you have this, it's not long until every car can sense around themselves and send that information. The Tesla can do it, obviously, and many other cars can do it. So that would provide great advantages, because now you could almost say, well, okay, so if cars can do this on board, like you see here, all I need to know is what's happening around me. And if somehow there's enough cars doing this, then technically what I've done in the middle could happen. Now, obviously, I'm not trying to sell this as something that's going to work tomorrow, but I think we will see it within a decade, and the underlying algorithms to do that are not trivial. So there's a lot of work to do here, and that's something we're interested to do. So this is a bit of a gloomy movie. Once I presented this at a conference, and they said, this is too morbid, you should remove this. But okay, I think this is UCLA and it's part of UC, and since it's allowed on the Berkeley campus, hopefully it's allowed in the LA campus. But this is kind of a provocative way of saying that, Deep RL has kind of killed Pong, and you've played that. If you're my generation, you probably played that when you were a kid, and you know how hard it is. So it actually managed to beat humans by just pixel learning. Then this is the famous AlphaGo competition, where again, a very unusual strategy led a machine to beat a human. And so, the real question is, well, how far can we do with traffic? I mean, obviously, we're going to solve the whole traffic problem that way, but there is great potential here. Maybe this being the only equation I'm showing, essentially all this is doing is essentially optimizing a reward with respect to a policy. And I would say 99% of the work we're doing there is experimental in nature. So essentially devising reward functions and architectures to support that. If you're interested, you can go to the Flow website, and there is a lot of examples to get started, but you can try it on Sumo or MSUN. We started with MSUN, but now we're mostly working on Sumo for various reasons, but it works on both. You'll find there all the different Lego blocks that can be used to get started, so get some proficiency with what we're doing. In fact, we did launch benchmarks at CORL in 2018. We initially viewed this as a form of Mujoko of traffic, so a place where people could come and experiment with their different algorithms. Since then, we've pivoted a bit, because for the project we're doing with Benny, John, Dan, and Benedetto, we are working now for the Department of Energy, and essentially our goal is to produce algorithms that will be demonstratively more efficient to smooth traffic. So we've created actually a dashboard that you see here, in which algorithms can be checked in, and then they can be experimented on the same traffic scenario, the I-210 I showed before. And you can see the improvement over time. This axis here is the time at which they were checked in, and what they produce in terms of smoothing, in terms of energy efficiency, and so on and so forth. And it's important to say that, for this to make sense, energy models are crucial. And so one of the things which is essential is, and that's really a nice joint work between the Temple campus and the Berkeley campus, Benny Siebold's team and my team are working very closely with models from Argonne National Labs to understand how sensitive these will be to the models. Because at the end, the result is only as good as the energy models of the vehicles, and there's a lot of difficult modeling issues here that we have to solve. And so I think part of our contribution here will be to demonstrate that not only does it work nicely in simulation, but that it does work nicely when energy is computed also within reasonable bounds, which is why the joint work we do with Temple is essential, and that's something where Ken Butts from Toyota and a lot of other partners in Argonne in particular are helping us with these models. And so typically, the way to look like is you'll see as we are becoming better and better, the results get better and better, but also noting that we're going to have more and more vehicle models to be representative of what's happening on a real freeway. The target being the I-24 in Tennessee, where hopefully we can deploy this in a not so distant future using a DanWorks testbed. We also want
Alex, I need to rush you a little bit because we're running out of time. So, okay, cool.
I have one more slide and I promise I'm done. But thank you for keeping the trains on time. I can see the Swiss trains are always on time. You did live in Switzerland at some point. So we also have done a bunch of workshops to train people. And so maybe in a not so distant future, we can do another one at IPAM, maybe when IPAM reopens beyond the digital world. And of course, finally, if you're interested in downloading Flow, it's all open source, so feel free to do so. We have already a nice user community. It's kind of nice. We do the best we can to help them. And then hopefully soon we'll be able to show algorithms also in the open source domain in circles, but that will not come before a little bit of time, because obviously that project still needs a few years before we can produce them. And I think this is it. So sorry for being late by a few minutes. If there is still time, I'm happy to take questions or just give you a little bit more free time for your coffee break.